Okay, today we are going to look at decline curve analysis, and we are going to see how we can use this decline curve analysis to do our prediction, to do the performance of our system or the performance of the reservoir, or to predict how the performance will be in the nearest future. The whole of this week, we have done relative permeability and how to draw the relative permeability curve and how to carry out nodal analysis. And then one thing I want to emphasize is if you're drawing the relative permeability of oil, make sure you use oil saturation to draw it. And then you make the adjustment that we did last session at the beginning. Because if you use water saturation to draw it, the curve will not come out well as mine. So you have to use the oil saturation to draw the relative permeability of oil. Okay, having said that, today our interest is more or less on the production decline curve analysis. So I'm just going to do a little bit of flip on what we call the production profile. This looks more or less like what is happening in an oil company. We always start from square zero, where there is no oil production. At this square zero is usually called the exploration stage. At the exploration stage, what is usually carried out is mostly surface geological surveys, analyzing samples to see how possible it is to have hydrocarbon, see if we have potential source rock, potential reservoir rocks, analyze the source rocks to see how matured they are. If everything proves successful, they may now carry out a seismic survey over a wide area. Then if everything also proves successful, they now narrow the area to a particular prospect, So at that stage now, we just generalize it as the exploration stage. If everything is successful, they now move into the appraisal stage, where they have to drill a discovery well, analyze well-logged data, carry out mud logging, do some preliminary reservoir analysis. And if everything is okay, they have to drill another well again to verify those things that they must have discovered, because you cannot just drill from one well and you just assume that everything is okay. All right. So if everything now becomes successful at the appraisal stage, they are now moving now in the real engineering part of it. At the engineering part now, we start first with development. Development simply means they have to start putting up the surface facility. They have to complete the well. They have to make sure that everything is intact. And then they start now with the production gradually. So at that point in time, that is when the first oil is recovered from the well. So from the development phase, production starts increasing gradually until now gets now to full production. The reservoir is going to produce to a point where it is at maximum production rate. No matter what you do, you cannot obtain any production rate that is higher than that. At that level, what is happening now is mostly reservoir management. So during the plateau phase, when the oil rate is constant, what they are usually doing at that moment is reservoir management, trying to see how they can put everything in order for the rate to remain at that level. But it will come a time where the amount of hydrocarbon in the reservoir is reducing, the pressure of the reservoir is reducing, so the reservoir can no longer produce at that rate again. So what happens now is the rate of that production starts declining. It will decline to a point where there's no longer any economic value of that production. So what they are going to do is they are going to abandon the well. Abandon the well involves blocking the well and blocking everything, and probably clearing the surface facility and all of that. But the decline phase is not just as simple as that. The reservoir may start declining and they realize that they need some extra push. They need some extra push or some extra energy to reinforce production. So what they will now do is, at this level, the reservoir is producing on the basis of its primary energy. That means you have some kind of gas expansion into the reservoir that causes fluid to be forced out of the reservoir. You have the rocks themselves expanding. You have pore spaces that are squeezing out as a result of drop in pressure. All of these various energy, we may have an aquifer that is pushing the hydrocarbon towards the wellbore and all of that. So all of these are all the various sources of primary energy that the reservoir has. It's natural energy that it has. But when this energy fails and the company feels that there is still enough hydrocarbon in the reservoir, they may now apply some extra energy, which may now come as a result of what we call secondary energy. This secondary energy comes in the form of water flooding. They have to drill some kind of a well. We have our production well, and then we have the water flooding well, or what they call the injection well. So they pump water into that well, and water gets into the reservoir and start pushing the hydrocarbon towards the production well. That's what we are going to see in the first class next week anyway, because we are going to do some water flooding analysis with Excel. All right, so my main interest of showing this is there are three basic types of flow regime generally when it comes to flow in porous medium. We have the steady state flow regime. The steady state flow regime is when the pressure does not change with time. Of course, that is rare, or even if it happens, it may happen just for a short while. The pressure does not change with time. With pseudo-steady state, the pressure changes with time, but it changes at a constant rate. That means if the pressure change is, let's say, 10 psi per second, we expect that every second the pressure has to drop by 10 psi. So it's actually changing at a constant rate. That is pseudo-steady. Then we have the transient flow regime. That is when the pressure is changing and the change is not constant. So you cannot actually know what the change will be in the next second because the change is not constant. So at this decline phase, there is a concept where we call the decline curve analysis that we can use to predict what the performance of this reservoir will be maybe in 2 years, in 3 years, or in 4 years, so that they can actually know what to do before it gets to a point of abandonment if they have to re-energize the system. So the reason why I took time up to explain the various flow regime is because this particular equation, which we call the APS equation, that is used to predict the future performance of the reservoir at this stage, that particular equation is valid only when we have boundary dominated flow. It doesn't, because during this period, the flow has not yet reached the boundary, so it is mostly transient. At the beginning of the flow is transient. It has not yet reached the boundary. Immediately it reaches the boundary, it is now either pseudo-steady or steady. At that point in time, we now say the flow is boundary dominated flow because the boundary is now having an influence on the pressure regime. Because remember that we start drawing down from the reservoir. When you start the production, there is a pressure disturbance that is created in the reservoir because at the beginning of the production, everything is at steady state. That means there is a fluid inside the column, and that fluid has the same pressure as the reservoir pressure. So there is no pressure gradient that is created. So fluid cannot flow from the reservoir into the borehole. So at that level, we have a steady state. When production starts now, they are now removing the oil from the wellbore. As a result of that, the wellbore flowing pressure now is dropping. When it drops now, that pressure gradient now is created. That pressure gradient that is created now causes fluid now to flow from the reservoir into the wellbore. So the pressure disturbance first of all starts from the wellbore, then migrates gradually into the reservoir. So it first of all starts from the wellbore, the region around the wellbore, goes to the reservoir, and then it finally gets now to the boundary of the reservoir at the stage of when it starts declining. So this particular APS equation is valid only for boundary dominated flow. It's not valid for transient flow. We may have some other advanced work that has been done, like we have the Blasingame equation that is now projected from this is just a projection of the Abs equation, because we now have situations where we can predict performance for transient flow. But this Abs equation is the simplest type of equation that was developed in 1945, and that particular equation is valid only when we have boundary dominated flow and the bottom hole flowing pressure does not change. If we have a variable bottom hole flowing pressure, that particular equation also is not valid. All right, so this is now the basic Abs equation that he developed in 1945. That's the basic Abs equation. If you look at that equation, Q there is definitely our flow rate. T is our time, that's Q our flow rate. B there has been defined. B there has been defined as B is defined as the decay constant, the decay rate. At what rate is that reservoir decaying with time? After 1 month, how has that pressure or how has the rate decayed? Has it reduced by 4%, by 5%, by 10%, by 20%, or whatsoever? So this B is called our decay rate. And then D now is just an exponent. All right. When D is equal to 0, if I take Q raised to the power 0, all of this becomes 1. So I have an equation that depends on B. If I now integrate this equation, it's going to give me this. It's going to give me, let me expand it a little bit. It's going to give me this equation. And this particular equation now is called the exponential decline model. If D is equal to 1 and I put D equal to 1 there, I'm going to have this equation, and this is the harmonic decline model. So harmonic decline model is when D equal to 1, exponential is when D equal to 0, and the hyperbolic is when D is sandwiched between 1 and 0. So if you look at it, it is only the hyperbolic equation that is very complex. It's only the hyperbolic equation that is very complex because it depends on B and D, but these equations depend only on B because initial flow rate, Qi is our initial flow rate, which we will definitely know that. So the only complex thing, the only unknown in this equation is our decay constant or our decay rate. That's our unknown here. So this hyperbolic equation is very complex. Most at times it's difficult. We cannot use Excel to predict for the hyperbolic case, but we can use Excel to do our prediction for exponential and the harmonic stage, for the exponential and the harmonic model. All right, so if I look at that, the first thing now will be, I have my data, I have different types of model. What model is the best model to do my prediction? That's the first question that you ask yourself. What model do I use? So what we are going to do now is to plot a graph of negative change in cure, all over cure, change in time, against cure. We look at the shape of the graph. From the shape of the graph, we will easily know if we can use the exponential model to predict the performance of that system, or the harmonic model, or the hyperbolic model. Now, if I have this equation as my exponential model, let's assume that we now have an exponential model. How do I go about this exponential model in order to estimate the value of B? Remember that they have given you a data of flow rate and time. I need to use that data of flow rate and time in order to obtain the value of B. From the value of B, I can use that now to get to do my prediction in the next 1 year, 2 years, or whatsoever. So what I will do now is, if you introduce ln on both sides of this equation, you easily obtain this equation. You easily obtain this particular equation if you introduce ln on both sides of the equation. It means that if I draw a graph of ln cure against T, I expect it to give me a straight line with a negative gradient. Why? Because I am seeing negative B here. So if I draw a graph of ln cure against T, it will give me a straight line. the gradient of that straight line will give me the value of B. Remember that we are comparing it with the standard equation of a straight line, y equals mx, y equals c plus mx. We are comparing it with the standard equation of a straight line, a standard equation of a straight line. If I draw a graph of y against x, the straight line, what is attached to x becomes the gradient. Then this value gives us the y-intercept. So if I draw a graph of linear against t, it will give me a straight line, and the gradient of that graph will give me the value of b. What if I know the cumulative production? What if the cumulative production has been given? If the cumulative production has been given, then what I would do is I would draw a graph of cumulative production against the rate. If I draw the graph of the cumulative production against the rate, I expect it also to give me a straight line. So from here, you can make cumulative production the subject. It will give us NP. NP is equal to 1 all over B, I think. Yes, if this one crosses, yes, 1 all over B, cure I minus cure I minus cure. Oh, anyway, yes, cure I minus cure. So if I draw a graph of cumulative production against cure, I expect that this value will be around here. So the gradient of that graph is going to give me 1 all over B. So our value of M in that case is 1 all over B. So that is what we will do for a decline case in order to get the value of our constant B, is value of our constant B. Now, what happens now if it is not declined? If it's not declined, it could easily be harmonic or hyperbolic. It will easily be harmonic or hyperbolic. Let me take this off. All right. So if it is harmonic, this is the equation of the harmonic. Remember, if we go back up there, we see that harmonic is when z is equal to 1. That gives us that equation. In that case, we draw a graph of cure against t. Remember, in this case, we are drawing a graph of log cure against linear t. Look at the axis. It is a linear axis, but this is a logarithmic axis because we are seeing ln here. But in this case, we will draw a graph of log cure against log t. If you draw a graph of log cure against log t, you use this formula, you'll be able to obtain the value of our constant B. We'll obtain the value of our constant B. So what we will do now is we are going to predict one case, then you do the other case at home. So if I take this, that's data 1. All right, so our first thing is to determine our model. How do we determine our model? We determine our model by calculating the negative change in cure all over cure, change in T against cure. So that's the first thing that we are going to plot. So I'm going to have, no need writing the heading. Let me just do the calculation here. So the first thing is we have change in cure. So if we are dealing with the first case, there is no change in cure. So I will start with the second case. I will put my equal to change in cure equal to negative change in cure is cure final minus cure initial divided by, that's my slash, divided by what? Let's come here and see. Divided by cure change in T divided by our cure. Hold on. I want it to appear like this. When it starts appearing like this, it gives us headache. So we have Okay, so we have negative into this minus initial divided by, close the bracket, divided by cure times change in T. Remember, change in T is 1 minus 0, and 1 minus 0 will always give us 1. The difference between the months is 1, 1, 1, 1, 1, 1. So we don't even need to bother ourselves and put that change in T. So we put like that, and then we calculate. We can now take it down and it do the calculation for all. We have the calculation for everything. All right, so that's the calculation. You realize that it is constant. Look at it, it is constant. If we go back to our model, it's going to supposed to give us a constant value of this against cure. The value is constant, but if we want to see it clearly, we can still draw it. There is still no qualms in drawing. So we take that, we go to our curve. We may take scatter plot. There is no problem with that. And then we take select data, we add. For the x-axis, we have cure. So this is my value of cure. I will press Control Shift and I press the arrow down. It copy everything down. I don't need to be stressing myself. Then I come here for y. I start down. I press Control Shift and I press the arrow up. It copies everything. So I have that. Where is our graph? Okay, that's our graph. So you see that based on this, it shows us that our best model to do that prediction is going to be the exponential model. The exponential model is our best model there. So we will go ahead now and do the calculation. I can shift this graph. I will right click and I want to move the graph. I can move chart. I will move chart to where it will create any other role here. I will just click no, not that one. New. Yes. All right. So it has moved it to chart 1. So I'll go back to my data. It has moved it to chart 1. All right. So if I know that it is exponential, what do? I draw a graph of linear against T. I draw a graph of linear against T. You don't need to go and start calculating linear. Don't go and start calculating linear. We are going to change the scale into logarithmic scale. So I will take this. No, let's take scatter. Let's take scatter plot. So we'll take we'll take this one. Then we select our data. We add. So our title, let's just say exponential. The x value is the time. So I take that, Control Shift and the arrow down. It copies everything. Then I go now to y-axis, which is my rate. Control Shift and arrow up. Copies everything. All right. Okay. So this is what it gives us. So this is the rate. This is the graph of how the rate varies with time. Remember, we can always adjust. You can even come here. We don't need to go right there. You can come here and add things. We add the axis title. We add the axis title there. This is our time. This is our time. We can draw it and expand. We can always change the size of this. We can always go to Home tab and change it, maybe to 18. Then we bold it so that you can see it clearly. Then here now is our rate here. You can always adjust it also. I was not adjust, but remember that this axis is supposed to be the log of cure. It's supposed to be the log of cure. So I'll come here, highlight, and then I will take, let me highlight it, and I'll take former axis. Once you open, I look at, you see here, logarithmic scale. Once you click on logarithmic scale, all right, so what we'll do is, they have removed 0. So they're just telling you that 0 cannot be plotted. Of course, we know that log 0 does not exist. So 0 cannot be plotted on a logarithmic scale. So that gives us what we expect when we draw the graph of ln cure against t. Remember, if it is this case, you are putting log on the y-axis and log on the x-axis. We want to draw now the equation of this line. I may just simply take right-click on it and add trend line. I look at the trend line, maybe linear, yes, linear is okay. And then I may take display equation on chart. Display equation on chart. So that's the equation of the trend line. Francis. Hold on, let me see. All right, so in this case, the trend line will not be the best method of calculating our gradient. So let's leave that. So how do we easily calculate our gradient now of this line? All right, so I'll come here now. I want to calculate the value of m. M, and then I come here, is equal to, we know that gradient is equal to the change in the y-axis all over the change in the x-axis. So I will write grade. I'll write grade. Well, let me say gradient. All right, so all right, it's slope. So the word that Excel uses is slope. So I'll take my slope there. I open the bracket. They have asked me to give the known y's. They have asked me to give the known y's. So to give the known y's, remember that on our axis, it is on our y-axis, it is the rate. It is the rate. So I will give, let me try something and see. The log of the rate, I take it down. I close it, then comma. They're now asking for the known x. X is our time. X is our time. So I'll take the time right down. Okay. I close the bracket. All right, so that's our gradient. That's our gradient. So our gradient is negative, but remember that there is a negative here. So if you take that, it means that our value of B is equal to, not B, that's not B, our value of B is equal to 0.0181. 0.0181. That is our value of B. That's our value of B. Now, how do we use this value of B now to do our prediction? We use this value of B. They have predicted for 111 months. So let's see how we can do prediction for more than that. Let me add another month there. Yes, maybe 100 or even 200 and all of that. So from here now, what I will do is I'm using this formula now to predict. I'm using this formula now to do my prediction. This is the formula to predict the flow rate since I already know the value of B. So that formula now is going to be the initial flow rate. That's the initial flow rate. We are at 1,000. The initial flow rate, that's the initial flow rate. So since I want to put a formula, I will put equal to. Since I want to put a formula, I will put equal to my initial flow rate, which is 1,000 exponential exp into negative bt. So it's going to give me, all right, that's where we are. Once you go there, the thing starts complicating. So let's take it down back and redo it. Oh, I didn't put equal to initial flow rate. Initial flow rate times, we could just put times, which is star, AXP into our negative B. What's the value of B? Negative B, we'll just click there like that, and the cell will enter there, times our time. That's our time there. Let me close it. I think there should be an issue somewhere. There is no way it can give us a value that is greater than that. So we have B. Oh, okay. All right, all right. So we are doing our prediction from this point. Yes, we do our prediction from that point. Once you do your prediction from that point, it's already telling you that anywhere along the line, all right, it's okay. All right, so from there, that's our prediction. So we have to take it down to do the calculation, but it's not doing the calculation. So we have to repeat. Let's repeat the calculation here. Let's repeat the calculation here and see what we have. We have initial, so we have equal to, we have initial, that's initial. All right, so we want to keep this initial constant. So instead of using this symbol, what we are going to do is we'll just approximate it to 1.29 because we want to keep it constant, times we have exponential into the negative of our decline rate, which is negative 0.018 times the time, that's the time there, then we close it and we do the prediction. So it's already telling us that we are already moving towards very, very low value of flow rate. So generally, even before the flow rate even gets to around this point below 100, it really becomes an issue. So there is even no need for you to start predicting below this level, because at this level, what we are going to realize is that the rate is already very, very low. So it becomes very difficult for you to predict, because at that point they must have already thought of alternative methods, or probably they have already used other methods of enhancing the production of the reservoir. All right. So what you are going to do is you are going to carry out similar analysis with this. I think this one is ending somewhere around 100. Yes. So you just continue from there. First, that's data 2. So you have to determine the model, the right model. Then you draw the appropriate curve to obtain the decay constant. Then from that decay constant, you can predict maybe 1, 2, 3, 4, 5, 6, or 8 months beyond that particular level, to see what you have. Now, if I want also to draw the cumulative production, I will change this back now to linear. Let me change this to linear. I'll remove the logarithmic so that it goes back to linear. Let's remove this guy. All right. So we know that definitely that is our flow rate changes with time. How do we now get the cumulative production? How do we get the cumulative production with time? So we have NP, the cumulative production. The cumulative production, we are going to give it in thousands of barrels. Remember, in petroleum engineering, they use M for thousand, double M for million. So you see units like million of standard cubic feet, mm, SCF. So that double M stands for million, one M stands for 1,000. All right, what is flow rate? Flow rate is barrel per day, and our production is supposed to be in barrel. So if I take barrel per day multiplied by day, if I take barrel divided by day times day, the day and day will cancel and I'll be left with barrel. So the easiest way for you to get the production is for you to take the flow rate times the number of days that we have. Of course, we have each month here, we are going to assume that each month is going to be 30 days. So it means that our cumulative production in this case is going to be equal to, I take this, times the number of days, which is 30 days. Then I'm going to divide it by 1,000, because I want it to be in, I want the result of this to be in thousand of barrel. So I'm going to divide it by 1,000, because I want it to be in thousand of barrel. Now, since I want cumulative, I am going to add it with the previous. We know that cumulative means that as you're gradually going down, you are adding everything above it. You're adding everything above it. So that's what the cumulative means. As you're going down, you're adding everything above it. So at this level, our cumulative is 28. So let's see. All right, this one now is 56. That means they have added everything. So it means that as you're calculating at this level, let me put it there so that you see the formula. It means that at this level of calculation, they have added, if you look up here, let me just highlight it so that we don't. If you look up here, you realize that in this space, they have added plus D3. What is D3? Cell D, and then down here we are seeing what? 3. So it means that Z3 is this particular value. It means that they have calculated the one for this value, then they have added this one to it. That's the meaning of cumulative. As you calculate the one for that particular month, you add the previous one to it. You add the previous one to it so that you can obtain the cumulative value. So from there now, if I take it down, I am sure that it will do the calculation for me. So if I take it down, I'm sure that all the calculations will be done right to the last value. All right. So that gives us our cumulative production. Now we want to also add our cumulative production on this graph so that we can see how the cumulative production is going. Select data, we add data. On the x-axis, we are still okay with our time. So we are using our time for x-axis. Remember, you can easily highlight all by taking Shift Control. Okay. So you can easily highlight all by taking Shift Control and the arrow. So this one is okay. Then for the y-axis, I have the cumulative production. So I will highlight this, Control Shift, and I press the arrow up, and it takes down everything. Then okay. Okay. Didn't plot. Select data. Let's redo it. Select data, we add. For the x-axis, we have our time. Control Shift down. We don't want to take it too down because these other ones, we added them there. So let's follow the procedure for this. Let's follow the procedure for this. We don't want to take it too down. So we are going to end where our data ended. Then that's okay. Then I now take for Y, I take this Control Shift and I press it up and it takes the value. All right. So that's our cumulative production. So what I will do now is I want to see, this is my axis of flow rate. How do I know this axis? I want to create another axis on this side for cumulative production so that it will give us the value so that we can easily see. So what I'll do is I'll highlight this, right click, and take format data set. Then I see primary axis and secondary axis. So I will take secondary axis, then it will create me a secondary axis for cumulative production here. So I will come back here now. I will take this. I will also include the axis for that. All right, if it's not showing there, you come here, you take axis title. All right, that's secondary. So that is it there that has appeared there. We can now adjust this as our cumulative production. So the cumulative production is capital N, small p. So you can increase the size and whatsoever. So this is telling us that as time is going, what is happening is as the rate is dropping, we have an increase in cumulative production. Remember, we are saying cumulative because we are adding everything. We are not saying that the production is increasing. Of course, rate cannot be reducing and production increasing. No, we are talking about cumulative production. So if you realize that the reason why we could not, I think I made an error with this data, I would have removed all this part from 60 down. I intended to do that and I forgot. So that it has to end somewhere around here. So that it ends somewhere around here. After you have calculated the value of B, you can now predict this part. If the flow rate is already getting to 0, so there is no way you can be predicting. How will you predict when the flow rate is already getting to 0? So the data would have ended around here, so that after you have calculated the value of B, you can now predict now this pattern in the next year, in the next month to come. When you predict this pattern, you also predict the cumulative production. So I'm already telling you what you do for the assignment. The assignment, I'll make sure that it ends somewhere around here, so that when you calculate the value of B, you can use the formula now to do the calculation. If it is exponential, you are using this calculation, this formula to calculate the flow rate in the nearest future. If it is harmonic, you are using this formula to calculate the flow rate in the nearest future. Please, I have said, let's forget about hyperbolic for now. It is only computer simulation that can simulate hyperbolic, because it depends on B and D. So it's very complex. So if there's any question, you can ask.